Hi everyone, this is Dr. Nak. Today we're going to learn about inverses and radical functions. Before we begin, let's talk about what our goals are. Goal number 1 for this section is finding the inverse of a polynomial function. Goal number 2, finding the inverse of a polynomial and radical functions with restricted domain. This section should not be too traumatic because we've done problems like these before in previous sections. But I think it's good to review how to find the inverse of a polynomial function, so let's start out with that. Let's first review the definition of a one-to-one function. So a function is one-to-one if any two inputs in the domain correspond to two different outputs in the range. More mathematically, it says that if x1 and x2 are two different inputs of a function f, then f is one-to-one if and only if f of x1 does not equal to f of x2. Now, those of you who are more visual, let's take a look at this graph. So this is just a standard graph for f of x equals to x squared, which is just a parabola. Now, I'm going to pick two different x values because look at it. It says if x1 and x2 are two different inputs of a function f, where my f is x squared. Okay, so which one do you want to take? You want to take negative 2 and 2? So if I take negative 2 and a 2, they're completely two different values, right? So let me just call this x1, and 2 becomes the x2. So right here, x1 certainly does not equal to x2. Now let's read the definition here. It says, if x1 and x2 are two different inputs of a function f, so we got those, we got x1 and x2, then f is one-to-one. This notation means if and only if the corresponding y values must be different. That's the same thing as saying f of x1 does not equal to f of x2. So let me just first plot where the f of x1 is going to be. So f of x1, pretend that that's straight, is here, right? And then f of x2 is right here. Okay, so in this case, we have f of x1 equals to f of negative 2, but our function's x squared. So you're going to have negative 2, whole thing squared, so this is going to be 4, right? And then f of x2, in this case, we have f of 2, which is same thing as 2 squared equals to 4. All right, now notice that these are the same. Okay, now look at the definition again. It says f is one-to-one if and only if its corresponding y values are different. But here, they're the same exact corresponding y values. So therefore, our function is not one-to-one. Now, let's also recall the horizontal line test. Do you all remember that one? It says if every horizontal line intersects the graph of a function f in at most one point, then f must be one-to-one. By using the horizontal test, we can say that this is not a one-to-one function because, let me just draw a straight line through these 2 points right here. Now notice that the line intersects the graph in more than one point. So that tells us that the function is not one-to-one. So I'm just going to include that in. So let me just go over it again. F is one-to-one if and only if x1 does not equal to x2, then f of x1 cannot equal to the f of x2, or it passes the horizontal line test. Now review number 2. We've learned this before. F inverse of x only exists if f of x is one-to-one. Now let's go back to this graph again. We just looked at the same graph. Now we just determined that the whole entire graph is not one-to-one because if I draw a horizontal line across it, it's going to intersect the graph in 2 points, not just exactly 1 point, right? However, what if I restrict the domain? Restricting the domain means you only care from 0 to up to 2. So let me just write that. If I restrict the domain to 0 on, I should say, then you're only looking at this piece of the graph here. You're not even looking at the left-hand side of the graph. So now if I restrict the domain, do you see that that function is one-to-one? because no matter where you're going to draw the horizontal line, it passes the horizontal line test because it only intersects the graph at most one point. So here's our conclusion. F inverse of x, D and E means does not exist on the whole entire interval from negative infinity to infinity. However, it will exist if I restrict the domain to from 0 to positive infinity. Or you can do from the other way, to 0 to negative infinity, then you're just looking at this piece of the graph, right? So this also becomes 1 to 1. Therefore, you can find the inverse function of that. Review number 3. We talked about the domain of f and the range of f, and then domain of f inverse and the range of f inverse. So if, let's just take an element x from the domain of f, then f is going to take this into the range of f, and then we call this guy f evaluated at x. Now the f inverse goes the other way around, right? So they're going to take the element from the range of f, and then they're going to take that to the domain of f. So this will be your f inverse of x, which means that the range of f is exactly same thing as the domain of f inverse, and then the domain of f is exactly the same thing as the range of f inverse. Is it coming back? I hope so. And now let's go with review number 4. Two functions f and g are inverses of each other if f of g of x equals to x and g of f of x equals to x. So given two functions, how do you check to make sure that they're inverses of each other? You compose f of g and then g of f, and then cross our fingers that they're both going to equal to x. Review number 5. The graph of a one-to-one function f and the graph of f inverse are symmetric with respect to the line y equals to x. Sorry, WRT means with respect to. So let's just take this graph. So let's call this blue curve to be f of x, and that we have a straight line y equals to x. Now, if I want to graph the f inverse function, then it has to be a mirror image to that with respect to that y equals to x axis. So, oh my goodness, I have to draw this out. Oh goodness. Does that look symmetric? Anyway, so pretend like this, right? So pretend that this whole thing is a paper, right? And then you want to fold this paper at this line y equals to x. So you fold it, and then you basically trace your f of x, and then you should get your f inverse of x. Review number 6. How to find f inverse of x given a one-to-one function f of x. Step number 1, interchange the role of x and a y. Step 2, if possible, solve for y explicitly. Explicitly just means that you better able to solve for y equals on the right hand side. Everything should be in terms of x or the constants. Okay, so if I have a y equals something involving x and a constant, and then another y flying around on the right hand side, that is not expressed explicitly. That's called implicitly. It's very rare that you cannot just solve for y explicitly in this class. However, that could happen. Now, what does it mean if I cannot just solve for y equals everything in terms of x? Well, that means that the inverse of the function does not exist. Step 3, rename the function y by f inverse of x. So assuming that we were able to solve for y explicitly, now I need to call this y by f inverse of x. Now, the final step is the most pain in the butt. But anyways, after we get our f inverse of x, what we need to do is we have to make sure that given f, where did it go? Our given f of x and f inverse of x are really inverses of each other. So how do I check is you compose f inverse of x and f inverse of f of x. Now, if they're both equaling to x, then yes, they are inverses of each other. Okay, so I think we're ready to do some examples, so let's start. Example 1, let f of x equals x plus 5 all over 3 and g of x equals 3x minus 5. So here's the question, is g of x an inverse function of f of x? Now, chances are 50-50, right? Your answer is either going to be yes, they're inverses, or no. But we're going to have to show our work to determine whether they are or they're not inverses of each other. Okay, so first, what do we need to do? What we need to do is we need to check f of g of x, is that going to equal to x? And then g of f of x, is that going to equal to x? If so, then yes, they're inverses of each other. All right, so with that said, let's check. Let's take one thing at a time. Let's go with f of g of x. Okay, so I'm going to work this step by step. So you have f of our g of x is 3x minus 5. All right, now let's take a look at f of x, and then you're going to replace his x with what's in the parentheses that we have going on in here. So if I need to color code it, let's just pretend that's one quantity. You basically replace 3x minus 5 in place of x. All right, so if I do that, then here what we're going to get is 3x minus 5, and then plus 5, whole thing divided by 3. So that's same thing as 3x minus 5 plus 5 over 3. Now, negative 5 and 5, they're going to cancel each other out. So you're going to have 3x over 3, cancel out the 3, and we're going to get x back. Looking good. All right, so now what we need to do is the other way around. We need to check, is g of f of x, is that going to equal to x? All right, so let's check. So we're going to have g of, now our f of x is x plus 5 over 3. All right, so next step, what you need to do is this. You need to look at function g of x and then replace his x with what's in the parenthesis that you're given here. So if I need to color code it, let me just take that, and then you're going to have to replace it in place of this x here. All right, so let's follow it through. So that's same thing as 3 times x plus 5 over 3, and then minus 5. So then this becomes, notice that 3 is same thing as 3 over 1, correct? So with that said, do you see that I can cancel out the 3's? Okay, so then what do we get? We're going to have just the x plus 5 over 1, which is just x plus 5, and then minus 5, which is going to give us x back. All right, so what we just discovered is this. Yes, f and g are inverses. Let's take a look at example 2. Find the inverse of f of x equals 6x cubed plus 5. Now, before we begin, remember that f inverse only exists if f of x is a one-to-one function. So first, since we're not giving any restricted domain, we need to determine whether our given function is one-to-one. Now, what do you think? I think yes, because look at the power function that f of x is going to mimic, right? So remember the power function, so f of x is going to behave just like 6x cubed, but in general, x cubed. Now, remember this graph of x cubed. Try to memorize all the basic graphs. It will help you a lot. Now, x cubed graph looks something like this. All right, so that means what? It passes the horizontal line test, so therefore, yes, our f of x is one-to-one. So I just checked, it's one-to-one, so let's begin. Okay, so step number 1, what we have to do is you have to interchange the role of x and a y. Now remember that y equals to f of x, right? So here what we need to do is we need to write x equals 6y cubed and then plus 5. That's your step 1. Now step 2, what we have to do is we're going to try to solve for y explicitly. Okay, so how do I solve for y? Well, I would like to subtract this 5 first. Right, so then what do we get? We're going to have x minus 5 equals to 6y cubed. So then I would divide this whole thing by 6. Make sure to divide the whole quantity of x minus 5 by 6. So then let me just flip this around. So that implies that y cubed equals x minus 5 whole thing divided by 6. Okay, so now we need to solve for y. So what do we need to do? You're right, we need to take the cube root on the both sides. Okay, so if I take the cube root, what we're going to get is y equals the cube root of x minus 5 all over 6. Now, we're able to solve for y explicitly because look at the right-hand side, right? Do we still have y variable flying around? No. So we're good to go. Now step 3, claim that y to be your f inverse. So I'm going to claim our f inverse of x to be cube root of x minus 5, whole thing divided by 6. All right, so let me just box that because I'm pretty sure we did this correctly. If not, we'll just cry together and try it again. All right, but anyways, let's go with step 4, pain in a butt. We check. Okay, so let's first go with, which way do you want to go first? How about f of f inverse of x? Okay, so let me also box our f of x because we need this one. Okay, so ready? This is going to equal to f of f inverse of x. So we're going to have cube root of x minus 5 whole thing divided by 6. Now what you need to do is you have to look at function f, right? And then replace his x with what's in this whole entire parentheses. Okay, so with that said, if you want me to color code it, I can do that. So I'm going to plug this whole chunk in place of here. All right, so let's do it. So this is same thing as 6 times cube root of x minus 5 whole thing divided by 6. Don't forget that exponent of 3 and then plus 5. So now what's going to happen is what then? So cube root and power of 3, they're going to cancel each other out because remember the cube root is same thing as the power of 1/3. So you multiply 3 and a 1/3, you're going to have 1, exponent of 1. So this is same thing as 6 times x minus 5 over 6 and then plus 5. All right, now again, use this trick. Don't complicate your life. Do not distribute the 6 to the numerator. Do not complicate your life. 6 is same thing as 6 over 1, right? Now, since these two guys are being multiplied, yes, you can cancel out the common factors. Now, be careful. If there is a plus instead of being multiplied, then you cannot cancel out the 6, by the way. But anyways, let me just kill the 6. All right, now it's looking prettier. So what do we got? We got x minus 5 and then plus 5, which is going to give us our x. Looking good. Now let's go the other way around. What we need to do is we need to check f inverse of f of x. So here, let me just write f inverse of f of x. F of x was 6x cubed and then plus 5. All right, so now what we need to do is you have to look at function f inverse, right? And then you're going to replace his x with what's in the parentheses. So if I have to color code it, this chunk, I need to plug this into wherever we see our x in f inverse of x. All right, so let's do it. So this is going to equal to cube root of 6x cubed plus 5 and then minus 5 and then whole thing divided by 6. So let's just keep simplifying this. We got cube root of, I can drop that parentheses there. I really didn't need to write it, but I just wanted to make sure that I'm plugging this whole chunk in place of x. That's the reason why I put the parentheses there. But anyways, this becomes 6x cubed plus 5 minus 5. So this just becomes 6x cubed and then divided by 6. Now what? We can cancel out the 6. So then what do we get? We're going to have a cube root of x cubed. Looking good. So this is also going to equal to x. So we have shown that our f inverse of x is truly an inverse function of our given function f of x. So I'm just going to write that out. So therefore, f and f inverses are inverses. There. All right, but anyways, please let me know if you have any questions about this. Let's take a look at example 3. The function f of x equals 2x plus 1 all over x minus 1, where x cannot be 1, is a one-to-one function. Find f inverse of x. Now, do you all see why x cannot be 1? Because look at the restrictions on the domain, right? the bottom can never go to 0. But if x is 1, then this is all going to go to 0 and we're in trouble. So that's the reason why we have x that's not equal to 1. Alright, but anyways, I'm already telling you that this is 1 to 1, so we are good to go. Let's go with step number 1. Interchange the roles of x and a y. So again, y equals to f of x, so we're going to write this as x equals 2y plus 1 whole thing over y minus 1. Now be careful here. Now you also need to change x does not equal to 1 to y does not equal to 1 as well. If you're going to change interchange the role of x and a y, you have to do it to the restriction part as well. Alright, so now let's go with step 2. Let's try to solve this for y. Okay, so the first step, what I would do is this. Multiply both sides by the LCD, which is y minus 1, or those of you who likes to do the cross multiplication, it's exactly the same thing. Alright, so but let me just do this in a proper way. So I'm running out of room. So what I'm going to do is I'm going to take the same, let me just rewrite the same equation here. And I'm going to multiply this by y minus 1. And then this whole thing by y minus 1. Alright, so that implies that we're going to have x times y minus 1 equals to 2y plus 1. Right? The only reason why I multiply by the LCD is so that I don't have to deal with fractions anymore. Okay, so now remember what we're doing. We're trying to solve for y, so I'm going to distribute the x to each term. We're going to have xy minus x equals to 2y plus 1. Now I need to bring all the y's on one side of the equation, so let's bring the 2y to the left of the equation by subtracting 2y. So then what do we get? We get xy minus the 2y minus x equals to 1. Alright, so I need to do next is add x to both sides because I'm trying to isolate the y on the left. So then we're gonna get xy minus 2y equals to 1 plus x. Okay, so now what, right? What I'm going to do is I'm going to factor out the y. You'll see why in a minute. I'm going to have x minus 2 equals to 1 plus x. Now, if I factor out the y, all I have to do is divide it by x minus 2 on both sides, then boom, we're done, right? So here, I'm going to divide this whole thing by x minus 2. X minus 2, so what we're going to get is y equals 1 plus x all over x minus 2. Now for step 3, let's claim that our new function y is actually a f inverse of x. So I'm going to claim that f inverse of x equals to 1 plus x all over x minus 2. Now be careful here. What is the domain of f inverse? Well, if I have a x equals to 2 on the bottom, it becomes undefined. The whole expression becomes undefined. So here, restriction is going to be x cannot be 2. Alright, so that's our f inverse all together with this restriction. So let me just box that. And then let me just box our f of x as well. Now the step 4, the most painful part in doing this. Let me get to the next page. Hold on. Alright, so what I just did was I just copied down our f of x and f inverse of x, including its restrictions. So let's go with step 4. We need to check. We got this. Alright, ready? So let's first go with f of f inverse of x. So here what we're going to get is f of f inverse is x plus 1 over x minus 2. Same thing as 1 plus x over x minus 2, by the way. Alright, so now what we need to do is we need to look at our function f and replace this x with what's in the parentheses here. So I need to replace these x's with this nasty looking expression. Alright, so then let's keep going. So this is same thing as 2 times x plus 1 over x minus 2, and then plus 1 whole thing over x plus 1 over x minus 2, and then minus 1. All right, so now we have to simplify. So to me, the easiest way is to multiply everything by the least common denominator, LCD. So in this case, our LCD is going to be x minus 2 because 1, same thing as 1 over 1. So its denominator is 1. And here we have x minus 2. Same thing down here. All right, so let me just write that out. Multiply by the LCD. In this case, it's going to be x minus 2. So let me just write this out. So I'm going to multiply here by the x minus 2, and I'm going to multiply the bottom by x minus 2. Now, what we need to do next is you're going to have to distribute the whole entire x minus 2 to each term. So this is the first term, that will be the second term. Now, notice that if I distribute the x minus 2 to this, our first term, then this x minus 2 and the bottom x minus 2 is going to cancel each other out. So that means that you're only left with 2 times the quantity x plus 1. Now, then if I distribute the x minus 2 to 1, then you're just going to have x minus 2. So let me try to write that out. So if I distribute that, then I'm just going to end up with 2 times x plus 1, and then plus x minus 2. Now I'm going to do the same thing for the denominator. So now what we need to do is I need to distribute this x minus 2 to our first term. Now if I do that, then do you notice that this x minus 2 and this x minus 2 is going to cancel each other out? So what you're left with is just x plus 1. Then what I need to do is I need to distribute this x minus 2 to 1. So here, be careful here, you're going to have a minus. Now quantity x minus 2, that parenthesis is very important. Okay, so I think we're good to go. So this is same thing as 2x plus 2. I'm distributing the 2 to each term. And then you're going to have a plus x minus 2 and whole thing divided by x plus 1. Now don't forget to distribute the negative sign to each. So then here we're going to have negative x and then plus 2. All right, so then what do we get? Now positive 2 and negative 2 is going to cancel each other out. So we're just left with 2x plus 1x, which is going to give us 3x all over. Now from the denominator, our x is going to cancel out, and you're just left with 1 plus 2, which is 3. Now kill the 3's, then boom, we got our x back. Now there is one more very important thing that you need to include. That is the domain restriction. Now if you're going from f of f inverse of x, right? So this is going to equal to x for every x in the domain of f inverse. So what we need to insert now is this. You need to put the restriction on f inverse of x. What was it? That same thing as x cannot be 2. So please insert that in. All right, so I'm just going to write it as where x cannot be 2. Very important. All right, so let me just box that. All right, but anyway, so now let's check the other way around. So what we're going to do is f inverse of f of x. All right, so then we got f inverse of f of x, which is 2x plus 1 over x minus 1. All right, now what we're going to do is we're going to need to look at f inverse of x and then replace his x with what's in the parentheses. So here, let me just color code it. So you need to plug this whole nastiness into this x and then this x. All right, and the domain restriction on this part will be the same domain restriction that you have for f of x. In this case, x cannot be 1. All right, but anyways, we'll take care of that in a second. So then let's keep going. So this is same thing as f inverse. So we're going to have 2x plus 1 over x minus 1 and then plus 1. Whole thing over 2x plus 1 over x minus 1 and then minus 2. If you want to write down the domain restriction right away, go for it. So here, I'm going to write it as where x cannot be 1. You always want to look at the argument of your either f inverse or f. So whoever that sits inside of the parentheses, that's the domain restriction that you have to take care of. All right, but anyways, Now from here, we're going to use the same trick. Let's multiply by the LCD. In this case, it's x minus 1. So I'm going to write LCD equals to x minus 1. So here we go. I'm going to multiply here by x minus 1. And then multiply this guy by x minus 1. All right, now what we're going to do is we need to distribute x minus 1 to each term on the numerator, and then we're going to do the same thing for the denominator. So here, notice that if I distribute the x minus 1 to our first term, this x minus 1 and this x minus 1 is going to cancel each other out, and what you're left with is just the 2x plus 1. And then we're still going to have to distribute the x minus 1 to 1. So in this case, we're going to have plus x minus 1. Now, whole thing over. Now, let's do the same thing. So we're going to distribute x minus 1 to our first term. So again, x minus 1 is going to cancel each other out. So we're left with 2x plus 1. And then what we need to do next is I need to distribute the x minus 1 to 2. But be careful, there is a minus sign in the front of it, right? So you need to take that into consideration. So you're going to have negative 2 times the x minus 1. So far, so good. All right, so now let's keep simplifying. Let me just go up here. So what do we got? We have 2x plus 1x, which is 3x. And then what's going to happen is that 1 and negative 1 is going to cancel each other out. So it looks like what we have left on the numerator is just 3x. Now on the denominator, let's take one step at a time. Let me distribute everything. So let me just extend this. So we have 2x plus 1. And now I'm going to distribute the negative 2 to each term to get negative 2x and then plus 2. All right, so then what's going to happen? We can cancel out the 2x and minus 2x. So here what we're going to get is 3x over, so what's left on the denominator? 1 plus 2, which is 3. Looking good. Kill the 3, kill the 3. So this is going to become x, where x cannot be 1. All right, so there we have it. So those of you who are more visual, here are the actual graph of our f of x, which is in green, and then f inverse of x, which is in red, and this line right here is y equals to x. Now, as you can tell, notice that our f and then f inverse are symmetric with respect to this line y equals to x. So visually, you can tell that these two are actually inverses of each other. Let's take a look at example 4. Find the inverse of f of x equals to x minus 5 whole quantity squared, where x is greater or equal to 5. Now, if you want to graph this with transformation, that's totally fine. So what I would start out with this, y equals to x squared. So you're just going to get basic parabolas at the origin at 0, 0. So here's 0, 0. And when x is plus or minus 1, and then your y value is going to be 1. When x is plus or minus 2, then it's going to become 4. So you got the idea. So our first very basic graph is going to look something like this. Now for the second graph, I'm just going to call it y, I could call it y1 equals to x minus 5 whole thing squared. So that tells us the horizontal shift. Now, which way do we need to go? I know it's a little tricky, but we're going to have to shift this graph 5 units to the right. Okay, so I'll write that out. Shift y equals x squared 5 units to the right. All right, so let's just move all the key points. Okay, so 0, 0 is going to become 5, 0. And then negative 1, 1 is going to become 4, 1. And then 1, 1 is going to become 6, 1. You get the idea. And I'm going to move this by 1, 2, 3, 4, 5. All right, and then I'm going to move this guy 1, 2, 3, 4, 5. Okay, so this looks like, oh my gosh. Okay, all right, fine. All right, that's not so bad. All right, so here it is. So that is our y sub 1 equals to x minus 5 squared. So we basically just graph this out by using the transformation of the graph. Now let's look at the restriction. notice that we already talked about this, but the whole entire parabola here, it's not one-to-one. So therefore, the whole entire graph, we cannot find the inverse functions of that. Now, however, if I restrict the domain, so this is telling you we only care from 5 on, right? X is greater or equal to 5. So basically what we only care about is this piece of the graph. That's all we care about. We don't care about the other side of it. I don't know, can you see this okay? Here we go. Okay, so that will be our f of x with our restriction. Now notice that that piece is one-to-one, because if I draw any horizontal line on that, the lines are going to intersect the graph only at one point. Okay, so now let's get down to business. All right, so let's go with step 1. What we need to do first to find the inverse is to change the roles of x and y. So here we're going to have x equals to y minus 5 squared, and then again, don't forget this part, y is greater or equal to 5. Now step 2, we're going to try to solve for y. Okay, so there are a couple ways that you can do, but to me the easiest way to solve this is by taking the square root on both sides. Okay, but you need to remember this property. So if I have something like x squared equals to k, and if I want to just solve for x, we realize that we're going to have to take the square root on both sides. So if I go square root of x squared, now on the right hand side, this becomes the plus or minus the square root of k. So here you're going to have x equals to plus or minus the square root of k. So please be careful with that. So you could just go from this step to this step. All right, you don't have to write down the middle step. Okay, so now if I'm going to take the square root on y minus 5 squared, then on the left hand side, you're going to have plus or minus the square root of x. So here, let me just go like this, so taking the square root. This implies that we're going to have y minus 5 equals to plus or minus the square root of x. Now from here, if I add 5 to both sides, then I can easily solve for y. Okay, so then let me just go one more step. So here what I'm going on, let me just flip this. We're going to have y equals to 5 plus or minus the square root of x. Now don't forget the domain restriction, where y is greater or equal to 5. Now notice that before we're able to just solve for y equals one function. However, look at this. Do you see that y can become into two different, completely different functions? One of them is y equals to 5 plus the square root of x. Another one is y equals 5 minus the square root of x. So I'm going to write that out. So this implies that either y equals to 5 plus the square root of x, or y equals to 5 minus the square root of x, right? So we have to pick and choose which one is the correct one. Now here comes the restriction. Y must be greater or equal to 5. Okay, so let's just analyze this real quick. Okay, so if I add some positive quantity to 5, and do you see that our output, which is y value, is going to be greater than 5? So for instance, if I plugged it in x equals to 4, then here you're going to have 5 plus the square root of 4, which is 5 plus 7, which is going to be greater than 5. Our y value is going to be greater than 5. That makes sense. This is the good choice. Now, let's take x to be 4 again. So the square root of 4 is 2, right? So in this case, if I go 5 minus 2, our y value is going to become 3, which is less than 5. So that will be a problem. So what we need to do is, with this restriction, I need to eliminate 5 minus square root of x. So I'm just going to go like this. Kill, bye-bye. All right, so therefore, it looks like our inverse function. So let me just write down step 3. So we're going to have to replace our y with the f inverse of x, which is going to be just the 5 plus the square root of x. Now I'm going to box this. So here is our f inverse. And where in the heck did my f go? Okay, f of x is x minus 5 whole quantity squared. All right, so now step 4. All right, so I just copy and pasted our f of x and then f inverse of x. All right, so let's check f of f inverse of x. So this is same thing as f of 5 plus square root of x. Now what I need to do is I need to look at function f and replace his x with what's in the parentheses. So in this case, what we're going to get is quantity 5 plus the square root of x and then minus 5 whole thing squared. So here, let me see what we get. I can drop that parentheses inside of the bigger parentheses. So here you're going to have 5 plus the root x minus 5 whole thing squared. Now I can cancel out the 5's. So here what we're left with is square root of x squared. In this case, we're going to have our x back. Looking good. Now let's check the other way around. F inverse of f of x. All right, so in this case, let me see. We got f inverse of f of x, which is x minus 5 whole thing squared. All right, we're going to do the same thing. Okay, so what we're going to do is we're going to have to look at function f inverse, right? And then replace his x with what's in the parentheses here. So let me just color code that. So I need to plug this in place of x. Okay, so we're good to go. So this is going to be 5 plus, don't forget that square root. And then here you're going to have x minus 5 whole thing squared. All right, so then what do we get? This is same thing as 5 plus square root of something squared just becomes something itself. So you're going to have just x minus 5. So now we can cancel out the 5's, right? And then, boom, what do we get? Exactly what we wanted, which is just x. Now, let's not forget to check for the restriction here. So let me just go back to f of f inverse of x. Yes, we got that guy to equal to x, but there should be a restriction, no? Because, look at it. F inverse of x is given by 5 plus the square root of x, right? So that means that our x value has to be greater or equal to 0 no matter what. So let me write here as x must be greater or equal to 0. Again, where comes the restriction is whoever that sits inside of the bigger parentheses. Okay, so if that makes any sense. Now let's go with f inverse of f of x. Now the restriction is going to be on the f of x. Okay, but look at f of x. F of x is nothing but a polynomial, isn't it? So that means that there are no restrictions. So we can just keep it the way it is. So here are the actual graphs of f of x and f inverse of x. Now we already went over how to graph the f of x. Again, notice that this is going to start from x equals to 5. So this point right here is x equals to 5. All right, now our f inverse of x. Now look at the domain restriction. We said that the domain restriction for f inverse of x is set of all x such that x must be greater or equal to 0. I'm going to write that out. So does it make sense? Is our f inverse graph, is it only defined from x equals to 0 all the way up to infinity? Yes, it does, because look at where the f inverse of x graph starts. It starts here when x is 0, so this point is right here, it should be 5. But look at the domain. Domain starts from 0 all the way up to infinity, which makes sense. And furthermore, these two curves are symmetric with respect to the line y equals to x, so visually we can determine that these two are inverses of each other. For example 5, we're going to play a different game. So what we're going to do is we want to find the domain of the radical function. In this case, we are given f of x equals square root of x plus 2 times x minus 3, whole thing divided by x minus 1. Now let's analyze this real quick. Since we're given the square root, whoever sits inside of the square root has to always be greater or equal to 0. Okay, so that's the restriction number 1. The radicand has to be greater or equal to 0. Now, another restriction will be this. Just forget about the radical sign, right? Just look at this fraction here. Or I should say rational expression. So we have a polynomial over polynomial, but when x equals to 1, it becomes undefined. So that will be our second restriction. So let's write these out. So restriction number 1, let's just go with the easier one. So forget about the square root, look at the rational expression. So in this case, we know that the x cannot be 1. Now let's take a look at restriction number 2, which is the radicand has to be greater or equal to 0 no matter what, which is x plus 2, x minus 3, whole thing divided by x minus 1 has to be greater or equal to 0. So restriction number 1 we're done with. We're done with that. Now this guy right here. Now when is the fraction is going to be greater or equal to 0? Which is positive, right? Or equaling to 0. So it means that either the top has to be positive and bottom has to be positive, because positive over a positive is a positive, or negative over a negative is going to be a positive as well. So how in the heck are we going to find this quotient to be positive? Now, there is a little bit of an easier way to do this. I'm not quite sure how the textbooks is explaining it. All you have to do is just make the chart. All right, so ready? So first what we need to do is this. What we want is get the x-intercept for this whole entire expression. So the x-intercepts are at x equals to negative 2 and x equals to 3. All right, and also the 0 of x minus 1 is x equaling to 1. So make that number line. You'll see why I'm doing that in a minute. Okay, so first let me just go with, so pretend this is the axis for x plus 2. And then this is the axis for x minus 3. And this is the axis for x minus 1. Next step, jot down the zeros. So the zeros of this is x equals to, or the x-intercept, same thing, negative 2. This guy is x equals to 3. Now this guy is not going to be an x-intercept. In fact, this is going to become the vertical asymptote. Do you see that? Because, look at it. When do we have a vertical asymptote? Is when the denominator goes to 0. So here, I'm going to have a vertical asymptote at x equals to 1. Which makes sense because look at the restriction number 1. We already said that x cannot be 1. And we already know that our f of x will never touch the vertical asymptote. So this makes sense. Now, anyway, so next step is this. Jot down all the x-intercept and a vertical asymptote in order. So the negative 2 will be the smallest. So let me just call this one negative 2. And then next one would be 3. So let me just jot down 3 here. And then 1 should lie between negative 2 and a 3, right? So let me just plot this guy to be just 1. Okay, so that's your step 2. Now step 3 is this. You need to determine on which side of the x-intercept or the vertical asymptote is going to become positive or negative. Now in order to do that, all you have to do is just pick some point that lies in here. Okay, so what's bigger than negative 2? 0, right? So if I plug it in, x equals to 0 in place of x, do we get a positive answer or negative answer? I believe that we're going to have a positive answer, right? So that's telling you that on the right-hand side of negative 2, everyone's going to be positive. So I'm just going to write it out as everything from negative 2 on are going to be positive. That means that the other side is always going to be negative because your graph is always going to go from either the negative to positive at the x-intercept. Okay, so now we're going to do the same thing for our x minus 3. So here, right, it doesn't matter which side you want to start out with. So if you want to take something smaller than 3, pick a test point. So the test point, what's smaller than 3? 0? Yeah, 0 is smaller than 3, right? So I'm going to take test point to be 0. Now, if I plug it in 0 in place of x, do we have a positive answer or negative answer? I think it's negative because I have a 0 minus 3. So that's telling you that on the left-hand side of 3, no matter what, everybody is going to be negative. So I'm just going to write it as all negatives up in here. And then if you don't believe me, pick some number that's bigger than 3 and plug it into x minus 3. We should get a positive value. All right, now we're going to do the same thing where the vertical asymptote is. So let's analyze when x equals to 1. So let's go with either side is okay. I don't know which way you want to go, but okay, so let's go on this side. So what is bigger than 1? Well, 2 is bigger than 1, so that's going to be my test point. My test point is 2. I'm going to plug that in. 2 minus 1 is positive 1. So that's telling us that on the right hand side of 1, our function is going to be positive, and then negative on the rest of it. Now you're like, what the heck is this going to do for us, right? So now I did not write the fourth line, which is putting everything together. So the very last axis is for x plus 2, x minus 3, and then whole thing over x minus 1. Remember that what we want is where this is going to be positive, right? This whole thing to be positive. So keep that in mind. Now, next step. Jot down all the important x-intercepts or vertical asymptotes in order. So this is -2, 1, and a 3. Okay, so now this is all you need to do. Let me just jot down the little dotted line here. Okay, now let's go from -infinity to -2. What kind of a sign we have? We have a negative times negative times another negative. So negative times negative times negative, that's a negative, isn't it? So here, from -infinity to -2, we're going to have negative altogether. All right. Now, let's take a look at the interval from -2 to 1. Okay, so we're looking at this region right here. Now, let's look at the sign chart. We have a negative times a negative times a positive, right? So negative times negative is a positive. Positive times a positive is another positive. So from -2 to 1, our function is going to be positive. Now we're going to keep doing the same thing for each of the subintervals that we're going to get. So now what we're talking about is between 1 and 3. All right, so what do we got going on here? Between 1 and 3, we have positive times negative times positive, right? So positive times a negative is a negative. Negative times a positive is another negative. So here, we're going to have negative. Your function is going to be negative between the interval from 1 to 3. Now we're going to do the same thing for 3 to positive infinity. Okay, so look at the sign chart. You have a positive times another positive. So that's going to be positive altogether. Okay, so now let's take a look. What we wanted was this whole quantity to be greater or equal to 0, which is same thing as where the sign is going to be positive. So where is it? From -2 to 1. But notice that 1 becomes the vertical asymptote. Okay, so keep that in mind. And then also from +3 to infinity, isn't it? So we can say that x plus 2 and then x minus 3, whole thing over x minus 1 is positive on -2 to 1, but you have to exclude the 1 because at 1 we're going to have a vertical asymptote. And then also on 3 to positive infinity. So guess what? This is going to be our final answer. So this will be the domain of f. So I'm just going to write it as domain of f is going to be in an interval notation, -2 to 1, open, and then union, close 3 to positive infinity. And that's going to be our answer. I don't think your textbook makes this chart, but to me, this is the easiest way out. So here is the graph of y equals to x plus 2 times x minus 3 divided by x minus 1. Please note that this is not the function that we're dealing with. Look at our function has a square root on top of that. But this, we're just analyzing this piece right here. So notice that we just discovered that, well, we're going to have a vertical asymptote at x equals to 1, which makes sense. All right. And then also from -infinity to -2, your function is negative, which means that your graph has to dip down below the x-axis, does it? here is my equals an increment of 2, right? Because it goes 2, 4, 6, 8, 10. So this will be at negative 2. Look at it. From negative infinity to negative 2, our function assumes all the negative values. All right. And then what about from negative 2 to 1? But there is a vertical asymptote at 1. That's why I don't include the 1 as our domain. So now look at it. From negative 2 to 1, all the graph is going to lie above the x-axis, which means that our function is positive there. Now from 1 to 3, let's focus on 1 to 3. So 1 is at the vertical asymptote, 3 is here because 3 is the x-intercept, isn't it? Let me just jot that out. So this is the x-intercept, which is 3, 0, and this should be negative 2, 0. But anyways, if I look at the interval from 1 to 3, 1, 2, 3, our function is below the x-axis. So that makes sense because we say that on an interval from 1 to 3, our function assumes negative values. Now what about from 3 to positive infinity, which will be here? 3 to positive infinity, it lies above the x-axis, so that means that our function is positive. Now here is the actual graph of our f of x, which is the square root of what we just graphed. Okay, so again, we do have a vertical asymptote at x equals to 1, right? So it's excluded from the domain. Now, we just discovered that the domain of f is from negative 2 to 1. So let's see, where's negative 2? Well, negative 2 is at this point. So it does make sense. Look at all the x values where the graph is defined. Our x value starts from negative 2 all the way up to 1, but it's never going to touch 1. So it makes sense. This piece makes sense. Domain of f is from closed negative 2 to 1 open. And then let's take a look at this point right here. Let me just write that out in case you can't see. So this is negative 2, and then this is x equals to 3, right? So we also said that the domain is also from 3 to positive infinity. Is that true? This graph is defined from all the x values from 3 to positive infinity. So, which makes sense. All right, I'm pretty sure that you had enough of this. So I'm going to stop here. Great job, everyone. And if you have any questions at all, please let me know.